Okay, we will discuss this theorem which is called as total uh, probability theorem. So in this theorem, the entire sample space S is basically divided into n disjoint events A1, A2 up to An of the sample space, so that the union of all the events I from 1 to n, it forms S, and at the same time they are disjoint, that is Ai intersection Aj will be phi if I is not equal to j. So if you divide the entire sample space into n disjoint events a1 to an, so that their union is sample space and they are disjoint, then the probability of an event b, is given by summation of I from 1 to n probability of b given ai into probability of ai. Okay. So this is basically what we call as divide and rule or divide and conquer approach. So where you partition the entire sample space into disjoint events so that their union makes the sample space and their intersection is empty. So if you do this, then the probability of any event B can be computed uh, like this. Okay. So by quantifying the effect of AI on B through probability of B given AI, so the theorem allows us to calculate the probability of B. Okay, and the proof for this is very simple. In fact, we have drawn a diagram here where we have sample space S, and this sample space S is divided into different events which are disjoint, and this is event B which I have taken. So in fact this B event, it overlaps with A1, A6, A2, A3, A4, A5, everyone. Okay, but these events A1, A2, A3, A4, A5, A6, they form disjoint events. So B in this case will be, I can write B as intersection of B with sample space, that is one and the same thing, and B intersection the sample space is basically A1 union A2 up to union of An, and it becomes A1B, which is A1 intersection B union A2B, which is A2 intersection B, and so on, union of A and B. Okay, and since your AI or disjoint, therefore AIB, they are also disjoint. Okay, that you can see from this figure. A1 to A6 they are disjoint, and if you take the intersection of A1B with A2B, A3B, they all are also disjoint. Okay, like if I say the intersection of A1 with B, then you get this much region. Okay, this is the intersection of A1 with B. Similarly, A3 with B is this region. Okay, likewise you have A2B, you get this region. This is the intersection of A2 with B, and similarly with A6, A5, A4. So if A1 up to A6 they are disjoint, then their intersection with B is also disjoint, and if all these are disjoint events, then in the starting we have discussed that the probability of B, which is the probability of this, I can say that probability of B is equal to probability of B intersection S is equal to probability of this, which is the probability of this. And since all these are A1, B, A2, B up to NB, they are disjoints, then the probability of their union is simply sum of their individual probabilities. So I can write it as summation of probability of AI into B, summation of I from 1 to N. And probability of AIB, which is AI intersection B, it can be written as, in terms of conditional probability, probability of I is equal to 1 to N, probability of B given AI into probability of AI. Okay, this is what we call as a total uh, probability theorem. Okay, and now next, with this much introduction of the probability, we will now come to random variables and then random process. Now if you look to the definition of random variables, a random variable is basically taken as a function. A random variable, RV, it is a function that maps sample space to real axis. Okay, this is what is the definition of a random variable. It is a function that maps the sample space to the real axis. Okay, so what it actually means is that a function in which the domain is sample space and the range of the function is the real axis. Okay, so each outcome of the sample space is mapped to a point on the real axis. So if you do a mapping like this, that function which maps the sample space points to real axis, real values, we call it as a random variable. Okay, so suppose like if you say in tossing a coin, you have two outcomes, head and tail, and this is R, real axis. Okay, if I map this outcome to some number, maybe 1, and head to 1 and tail to some other number, maybe 0, or you can say -1, then this function which takes the points from the sample space and assigns a real value to each point in the sample space, this function is basically called as a random variable. Okay, a simple example of a random variable is like this. So we have experiment, you have some outcomes, and each outcome is mapped to a real number. Okay, likewise if you uh, roll a die, so you have 6 possible outcomes, zeta 1, zeta 2 up to zeta 6. So if I define x as a random variable, which is the number which appears on the dice, then of course zeta 1 I can map it to the random variable. In this case can take values from 1 to 6, 1, 2, 3, 4, 5, 6. So zeta 1 is mapped to 1, and zeta 2 is mapped to 2, and so on, and zeta 6 is mapped to 6. Okay, this is another example of a random variable. In fact, if you see a more simpler example that I can give of random variable is, suppose we have a exam, okay, of a particular subject, and there are certain students in the class, okay, maybe we have 50 students in the class. So you have roll number 1, you have roll number 2, roll number 3 up to roll number 50, and in this case the random variable I define is simply the marks that are obtained by the student in the class test or in the exam. Okay, so in this case we have a range of values on the real axis. Maybe the minimum is 0 and the maximum is suppose 26. The random variable that I define in this case is simply a function which maps each point in the sample space. In the sample space now we have candidates, their names or their roll numbers, and that point is simply mapped to a point on the real axis, which is basically the marks which are obtained by the student. Okay, so if suppose roll number 1 has obtained 10 marks out of 26, so I map it to 10. Okay, likewise roll number 2, it has obtained maybe 12 marks, so I map it to 12, and so on. So this mapping from the sample space to the real axis, this is what we call as a random variable. Okay, so when you define the random variable, we generally denote the random variable with x, and the values which the random variable can take is xi, so maybe x1, x2, up to so on. So if the values which the random variable can take, if they are discrete, then of course we have a discrete random variable. It is finite. Okay, if the range of the values which the random variable can take is continuous within a given range, then of course it is a continuous random variable. Okay, so the probability of xi is the probability of the random variable x having an equal value which is equal to xi. This is how we plot the probability density function or the PDF of the random variable. So x is a random variable which is not basically a random, which is not variable. X is basically function. Okay, it is a misnomer in fact. So which takes the points from the sample space and maps each point in the sample space to a real number on the real axis. Okay, I have taken 3 examples of the random variable. So each value which the random variable can take has a certain probability of xi. Xi is any value on the real axis in the range of the function. Okay, so like in this case xi can be any value between 0 and 26. In the case of rolling a die, x can be any value between 1 and 6. Of course we have 6 discrete values, either it can be 1 or 2 or 3 or 4 or 5 or 6. In the tossing a coin you can have only 2 values, xi can be either 1 or minus 1. The probability of xi is basically the probability of random variable x having value equal to xi. So if you plot the probability of this, you have probability of x on this axis I have x. So in this case you have only 2 outcomes, either this can take a value of 1 or minus 1, and the probability of both is 0.5. So this is the PDF or the probability density function for this random variable. Okay, likewise if I take this case, in this case your x can take values from 0 to 6, 0, 1, 2, 3, 4, 5 and 6, and probability of x, this is x, this is the probability of x. Again, in rolling a die, you know that if you have a fair die, okay, then the probability of occurrence of each number is same, which is 1 by 6. So the probability of each is, probability of getting 0 is 1 by 6, the probability of getting 1 is also 1 by 6, and so on. In fact, the sum of all these probabilities, summation of probability of xi over I, that should be equal to 1. Okay. Likewise, in this case, if you want to draw the probability density function, so on x-axis, on this axis you have x, on this axis we have probability of x, or you can add xi and probability of xi. So in this case, xi, which is the values which the random variable can take, and range from 0 to 26. So you have 0 to 26, you have 27 different values, either 0 or 1 or 2, 3, 4, and so on. Okay. Now the probability of getting 0 in this case will be basically defined by that how many points in the sample space are mapped to 0. Okay. Like none of the students suppose obtain 0 marks, then there is no mapping with the 0, and the probability of getting 0 is 0. Okay. So suppose there are 3 students who has obtained 1 marks, so they are mapped, all of the 3 they are mapped to 1. So probability of getting 1 will become basically 1 by 50, where 50 is the total number of students. Okay. And likewise, you can have probability of 2. Suppose no student has 2 marks, the probability of 2 is 0. Suppose you have 5 students who has obtained 3 marks, then the probability of 3 is 5 by 50, and so on. Okay. So if there are suppose 10 students who obtained 15 marks, then the probability of 15 will be 10 by 15. This is how you can plot the PDF of the discrete random variables. Okay. So you conduct the experiment, and then you define a function which maps the outcomes of the sample space to the real axis, to the real numbers. Okay. And then you can find the probability of xi, where xi is the values which the random variable can take. Okay. Likewise, if you have suppose I can take one more example. Suppose if you have a digital image, maybe you have a digital image with a size of suppose 16 cross 16. That means we have total 256 pixels in the image. Okay. And if it is a 8-bit image, so in the 8-bit image you have 2 to the power 8, which is 256 different intensity levels. Okay. So you have 16 rows and 16 columns, and each element of this matrix represents a pixel element. Okay. So if you want to find the PDF of this image, so we have again here x and px of x. So x in this case can range from 0 to 255, because we have 256 intensity levels. So the image intensity can be anything, it may be 0 or 1 or 2 up to 255. When it is 0, it represents the black. When it is 255, it represents white. In between, we have different shades or intensities. Okay. Now, when I say the probability of 0, the random variable getting a value of 0 is that how many pixels in the image have intensity value equal to 0 divided by total number of pixels. Okay. So suppose you have 5 pixels in the image with the intensity level of 0, then the probability of 0 is 5 divided by 256. Okay. Likewise, suppose we have 128 pixel intensity. So there are suppose 50 pixels in the image with the intensity of 128. Then the probability of random variable taking a value of 128 is 50 divided by 256 and so on. Okay. This is how we get the PDF of the random variables. Okay. So one more example you can say that suppose two dice are thrown and the sum of the points appearing on the two dice is a random variable x. Okay. Two dice are thrown and the sum of points on the two dice appearing on the two dice is a random variable x. So what are the values that can be taken by x and their corresponding probabilities? Okay. So xi, if you see, if you throw two dice and the sum of the points on the two dice is a random variable. Okay. So if you see the possible outcomes, the dice outcomes can be 1 1. It means this number 1 appears on the first and the number 1 also appears on the second dice, or it can be 1 2 and 2 1. So xi, which is the sum of the points on the two dice, that is what I am defining as a random variable. Okay. It means in this case, the first case, this can take a value of 2. The minimum value is 2. Okay, because the minimum number on each dice is 1. So the sum of the two numbers becomes 2. Or it can be 3 when it is 1 2 and 1 2. The sum can be 4. In this case, we have three possible outcomes. Of course, it can be 1 3 or 2 comma 2 or 3 comma 1. Okay. Likewise, the sum can be 5. You have 1 4 or 2 3 and 3 2 and 4 1 and so on. The maximum number that can appear is 12 when you have 6 and 6 on both the dice. Okay. And there here I say probability of xi. So probability of xi x, or again probability of x is equal to 1 is of course 0. Probability of x is equal to 2 will become 1 by 36. Okay, because we have 36 different combinations and the probability of getting 2 is 1 by 36. Because when you define the random variable, again I suppose I have a real axis, then these are the sample space points. So I map each sample space point on the real axis. The minimum value is 2, the maximum is 12. So this is mapped to number 2. When you have 3, so this outcome and this outcome, they both are mapped to 3 because the sum of the two numbers on the dice is 3. Okay. Likewise, these three outcomes, they will be mapped to value of 4 and so on. This is what is the mapping. Okay. You have sample space, you have real axis. The sample space points are mapped to the real numbers on the real axis. This is what we call as random variable. And then we define their individual probabilities. So probability of getting x is equal to 2 is 1 by 36 because there is only one out of 36, only one sample space outcome is mapped to 1. Similarly, the probability of x is equal to 3 will be 2 by 36. Probability of getting x is equal to 4 will become 3 by 36, which is 1 by 12. This I can write 1 by 18 and so on. and probability of getting x is equal to 12 is again 1 by 36. So again, if you find the sum of all these probabilities, it should turn into 1. Okay, so this is how you define a random variable and how you can find its PDF, the probability density function. Okay.